Hello everyone. Today we are going to discuss about divide and conquer. It is widely known topic. This is Anirudh and Kartheek presenting you for today. The context for today's presentation is first we are going to discuss the definition of divide and conquer with an example. Later on we are going to continue with merge sort, which is an application of divide and conquer. As we continue, we are going to look into recurrence equations, guess and test method, master method, and few more techniques. The definition of divide and conquer is the technique that involves breaking down a problem into a smaller subproblems, solving them independently, and then combining their solutions to solve the original problem. This is used to solve complex problems by making them smaller problems and finding solutions to the subproblems and combining to solve the original problem. There are many more of such techniques. Few are backtracking, dynamic programming. For problem solving like sorting and searching, divide and conquer is the best approach. This is the pictorial representation of how divide and conquer work. The base case for the recursion are subproblems of constant size. The divide and conquer is done recursively. The analysis of divide and conquer can be done using recurrence equations. Coming to the example of divide and conquer, we consider a raw data input and dividing it into subproblems. After division of each and every input into a single element, we merge the data in whatever the order we require. It can be sorted order or anything else. Next, we have a well-known application of divide and conquer, which is merge sort. Merge sort is a recursive method that progressively divides an array into half until it can no longer be divided. Following the division of the array till it becomes a single element. The sorted subarray that have been sorted are then combined into a single sorted array. As presented here, we can see the merge sort algorithm, which is same as we discussed. We can understand the running time and complexity using recurrence equation analysis. As we saw the algorithm in previous slide, we consider two cases. The first one is when the size is less than 2. In this case, the running time is considered as constant as it has only a single element. In the next case, the running time is given by 2 of t n by 2 plus bn. We can analyze these equations and find the complexity by finding closed form equations. We can solve these equations by iterative substitution method. Iterative substitution is basically a divide conquer strategy that entails repeatedly applying and recurrence equations to itself in order to find the pattern. So by substituting value t of n by 2 in t of n and by solving it, we can get 2 power I t of n by 2 power I plus ibn. This is like a general equation after solving. To get the base case, we can get it by substituting 2 power I is equal to n. So from this equation, we can write t of n is equal to b into n plus bn log n. From this, we can say that the time complexity of the equation is O of n log n. We use recursive tree for visualizing the process that happens when a recursion is iterated. By drawing the recurrence tree from previous recurrence equation, we can see the pattern. That is, time taken to divide is b of n, and the total time taken is given by bn plus bn log n. Not just with the iterative substitution method, we can also find the time complexity using guess and test method. It is a very powerful tool for solving recurrence equation. In this method, we guess a closed form solution and then try to prove it by induction method. From previous slides, as we derived the above recurrence equation, we can see T of n is equal to B when n is less than 2, 2T of n by 2 plus Bn log n when n is greater than 2. As our first guess, using inductive hypothesis, we take T of n is less than Cn log n. By substituting this equation in T of 2T of n plus Bn log n, we get Cn log n minus Cn plus Bn log n, which we can say that it is greater than Cn log n, as Bn log n and Cn both terms are present in the equation. But as it disproves our guess, which is Tn should be less than Cn log n, we can say that our guess is wrong and we have to guess again.
Hi, I am Karthik. I'm going to continue from here. And this is the second example of guess and test method. And these is a recurrence equation where n should be less than 2 if t of n belongs to B, and n should be greater than or equal to if t of n belongs to 2 times of t of n by 2 plus Bn log n. And the second example is second case is t of n should be less than or equal to Cn log square n. I'm going to substitute this term in t of n. Then after substituting, I will be getting 2 times of C of n by 2 log square n by 2 plus Bn log n. So after solving this, I'll be getting less than or equal to Cn log square n, which satisfies the condition. And the time complexity of this term is order of big of n log square n. And there is a master method which is used to solve recurrence equations, which is a best topic in divide and conquer. So T of n is equal to C if n is less than D, and we are going to use this a times of T of n by B plus f of n term to solve recurrence equations. With some examples we are going to solve. And if it satisfies only if n greater than or equal to D. So we have three theorems below here, which is the first case is f of n should be order of n power log a minus epsilon to the base b. If and only if then t of n belongs to theta of log n, theta of n power log a to the base b. And the second theorem is f of n belongs to big theta of n power log e to the base b and into log power k times n. So then theta of n belongs to big O theta of big theta of n power log e to the base b times of log n, log k plus n to the n. And the third theorem is, so f of n is omega of n power log a plus epsilon to the base b. Then the condition will be t of n is theta of f of n. So this satisfies only if a times of f of n by b less than or equal to delta of f of n. So for some delta is less than 1. And on the next is we are going to solve the examples. On the first example is t of n is equal to 9 times of t of n by 3 plus n, where a is equal to 9 and b equal to 3 and f of n is equal to n. So we're going to take n power log e to the base b formula to get the time complexity, and it is equal to n power log 9 to the base 3, which gives me theta of n square, order of n square. And I have to prove that f of n is less than or equal to the term order of n square. So I'm taking f of n equal to order of n power log 9 to the log 9 minus epsilon to the base 3. For epsilon equal to 3, I'm assuming. So in this case, the case one applies, like satisfies the theorem. So the order will be order of n square. Time complexity will be order of n square. And the next example is t of 2n by 3 plus 1, where a equal to 1, b equal to 3 by 2, and f of n equal to 1. And I am again using n power log e to the base b, which gives me n power 0, which again equals to 1. And ff1 is equal to theta of n power log e to the base b, which satisfies the second case theorem. And the time complexity of this theorem is order of theta of log n. And the third example is 3 times of t of n by 4 plus n log n, where a is equal to 3 and b equal to 4 and f of n equal to n log n. So the formula is n power log e to the base b equal to n power log 3 to the base 4, which gives me theta of n power 0.793. So I'm assuming epsilon equal to 0.2, for which the formula before is f of n is equal to omega of n power log a plus epsilon to the base b. So I'm substituting the values. We'll be getting omega of n power log 3 plus epsilon to the base 4. So after substituting epsilon equal to 0.2, I'll be getting omega of n power 0.83. So on this omega complexity satisfies only if you show that a times of f of n by b is less than or equal to delta of f of n. So after substituting the values, I'll be getting 3 times of n by 4 log n by 4, which is less than or equal to cn log n. So after substituting 3 equal to 3 by 4, sorry, c equal to 3 by 4, the condition satisfies. And the next is iterative proof of this master theorem. I'll be using this theorem for the proof of master's theorem. So let us take a pattern of t of n equal to a times of t of n by b plus f of n. I'm substituting this t of n in this t of n by b, then I'll be getting like equation like a square t of n by b square plus a times of f of n by b plus f of n. So after doing multiple substitutions, I'll be getting a geometric series of n power log a to the base b times of t of 1 plus a power I times of f of n by b power I, where I belongs to 0 to log into the base b minus 1. So the first term is dominant and the lowest term is the geometric series. And the next topic that I'm going to teach is integer multiplication. So integer multiplication is a product of two integers. So here I'm taking I and j to be a two integers, which is higher order and lower order. So let us think I equal to ih times of 2 power n by 2 plus I1, and j equal to jh times of 2 power n by 2 plus j1. So I'm multiplying both this I and j. So I'll be getting the term IH 2 power n plus IHJL 2 power n by 2 plus ILJH 2 power n, sorry, ILJH times of 2 power n by 2 plus I1 J1. So for example, if I take t of n equal to 4 times of t of n by 2 plus n, then the time complexity I'll be getting is order of n square. The next on the next one is this is an improved integer multiplication algorithm, where I'll be doing this multiplication in a different way. So I'm taking the two equations as the same and I'm multiplying in the another way. So where I'm multiplying I and j is equal to IH JH to power n plus IH minus IL into JL minus JH plus IH JH plus IL JH times of 2 power n by 2 plus IL JL. So after multiplication and IL JL and IH JH will be cancelled up, and at the final I'll be getting IHJH 2 power n plus IHJL plus ILJH times of 2 power n by 2 plus ILJL. So for example, if I take t of n equal to 3 times of t of n by 2 plus n, so which gives me order of n power log 3 to the base 2. So which gives me order of n power 1.585. And the next, the applications of divide and conquer is the first one is defective chessboard, and the second one is binary search, and the third one is Tressen's matrix multiplication.
And also merge sort, quick sort, and Kartheek algorithm for the fast multiplication. These are the applications of divide and conquer. Thank you for listening. Have a nice day. This is Anirudh and Karthik. Thanks for having us today.
Thank you and have a nice day. I'm Karthik.